In this video, I want to walk you through some of the basic conclusions we reached from our periodic motion lab. In our periodic motion lab, we were looking at the behavior of spring mass systems that were basically oscillating, moving up and down in a periodic or cyclic way. And we wanted to find out how the mass of the system affected its period, how much time it takes just to go through one full cycle. So students changed the mass of their spring mass system and measured the period in seconds. And to answer the question of how mass affects the period, they graphed mass on the x-axis and period on the y-axis. In the experiment, we had different groups use different color springs, which all had different spring constants. And so let me show you some of the results that we found and talk about some of the conclusions we reached together when looking at those results. So just comparing some groups that used the red spring to the green spring, we found out that when we graphed period versus mass, so as mass increases, we looked at period, all of the groups found that we had a side-opening parabolic relationship, so it wasn't linear. So as mass increased, the amount of time it took to go through one cycle did not increase also in a linear way. When we looked at the green spring, that was also the case. And so every group ended up squaring what was on their y-axis, taking the period squared and graphing that versus mass, because in order to linearize a side-opening parabolic relationship, you've got to square whatever's on the y-axis. And so each group ended up doing that to get a linear relationship between two different variables, period squared and mass, so that they could write the equation for how period is related to mass. So looking at the green spring, if they graphed period squared versus mass, their equation looked like this. Period squared equals the slope times the mass. And for the green spring, they got a slope of 0.893. And the other group that used the green spring, they also found a very similar slope. The groups that used a red spring, they found similar slopes, 1.84 or 1.58, pretty close. And we noticed that both red springs had a higher slope value than the green springs. And what was different about the red spring and the green spring? Well, the green spring had a spring constant of about 50 newtons per meter. That was its K value. And the red spring, its spring constant or K value was about 25 newtons per meter. So we noticed that the higher slope values had smaller spring constants. There's kind of like it's somewhat of an inverse relationship between the two. And so this is not the spring constant, this value of the slope, but it's apparently related to the spring constant. We also decided that the y-intercept in the graph of our linearized graph was insignificant. A lot of groups found that their value for the y-intercept was less than 5% of their biggest value on the y-axis, or their period squared value. And we also talked about the fact that logically we could think that as the mass decreases and it gets really, really, really small and approaches zero, we would expect the amount of time it takes for that mass to go up and down once, or its period, to also approach zero. So our equation just looks like period squared equals something times mass, and the slope, or that something, is related to the spring constant. So we needed to do a little bit more work to figure out what in the world our slope actually represents, so we can get a general equation which tells us how the period is related to the mass for any spring that's used, whether it's a red one, a green one, a yellow one, or any spring constant. So in order to do this, we need to do a little bit of experimentation and manipulation with this equation. So we know that this number is related to the spring constant in some way. So I'm going to actually end up multiplying the right side of this equation by 1, and that wouldn't change anything. Well, rather than just using 1, we could take something divided by itself that's also equal to 1. And why am I using 50 newtons per meter? Well, that's the spring constant, or the K value, for the green spring. So if we take the right side of the equation times 50 newtons over meter divided by 50 newtons over meters, that doesn't really change this equation, but it allows us to figure out, kind of pull out the spring constant value, because we know that this number is related to that. And the bigger the spring constant, the smaller the number. So we should expect that the spring constant, or the K value, will show up in the denominator somewhere in this equation. So we're going to replace this bottom 50 newtons per meter with K, just the symbol which represents the strength of the spring constant. And so now we have 50 newtons per meter on top times the experimental value for the slope times mass divided by K. And I'm just going to group the numbers and group the symbols together. So we get 50 newtons per meter times 0.836 seconds squared over kilograms. These were the units of our slope from our period squared versus mass graph. And then we have mass, the symbol for mass, divided by the symbol for the spring constant. So let's combine these things together. 50 times 0.836 is about 41.8. And the units, nothing cancels yet. There's newtons times seconds squared on the top, divided by meters times kilograms on the bottom. So we've got that now for our units. So we now have an equation that says period squared is equal to something times the mass of the spring mass system divided by its spring constant. And we need to figure out what is that something. Well, the units are often a clue, so let's see if we can simplify these units to help us figure out the identity of what this value is, or what it represents. So we take the slope units, which are newtons times seconds squared, divided by meters times kilograms. And remember, the definition of a newton, that a newton is equivalent to a kilogram times a meter over second squared. You can prove that to yourself just by thinking through the units in Newton's second law, that a newton per kilogram, a force, sum of the forces over mass, gives us an acceleration, which is meters per second squared. If you solve that for newtons, you see that newtons is the same thing as kilograms times meters over second squared. So now we have all of that multiplied by seconds squared, divided by meters and kilograms. And now, man, a lot of things cancel. So we can see that there's a kilogram on the top and the bottom, they cancel. There's a meter divided by meter, the meters cancel. And here we have seconds squared divided by seconds squared, those also cancel. So it turns out that this whole mess of units turns out to cancel out, and it shows us that that number is unitless. You might think, well, that doesn't really help us out in understanding what it represents, but it actually does, because if this number is unitless, it can't represent something that can be measured, a length, an acceleration, a gravitational field strength, or anything else, and a certain amount of energy. So let's look at our equation. We get 41.8 times the mass divided by the spring constant is equal to the period of our spring mass system squared. Well, let's get a general equation not just for the period squared, but for the period. So we want period equals something. So I'm going to take the square root of both sides. And on the left side we get just period. And on the right side we get the square root of 41.8 times the square root of mass divided by the spring constant. The square root of 41.8 is 6.46. So our general equation is the period of a spring mass system is just equal to 6.46 times the square root of mass divided by the spring constant. So here's the question. Can we take it any further? The question is, what unitless constant has a value around 6.46? Or what unitless constant is there that this is a multiple of? Well, 6.46, that's awful close to 6.28. And what is 6.28? That's 2 times 3.14, or about 2 times pi. It turns out, 2 pi is 6.28 approximately. So our unitless number is 2 pi. So the general equation for the period of any spring mass system is just 2 pi period equals 2 pi times the square root of the mass of the system divided by the spring constant of that spring mass system. So this is one of our AP Physics 1 equations, and it looks like this on our AP Physics equation sheet. And capital T, remember, represents the period, the time for one full cycle. M represents the mass of the system in kilograms, and K represents the spring constant of that spring in units of newtons per meter. Now, one note about the K in this equation, or any of the equations that we have that deal with springs. So here's 3 equations we have now at this point in the class which help us think quantitatively about springs. The force exerted by a spring is equal to its spring constant times how far it's displaced from equilibrium, either stretched or compressed. Here's our new equation for the period of an oscillating spring mass system. And we also talked about the equation which allows us to calculate the amount of energy stored in the spring potential energy account if we know the spring constant and how far it's compressed or stretched squared. Now, all of these equations are assuming we're using ideal springs, that the strength of the spring is constant. Well, remember, how do we even define the spring constant? Back in our spring force lab, we looked at how the stretch of a spring was related to the force it exerts. And we found out that for our springs, there was a linear relationship between force and stretch, or force and compression, depending on what kind of spring you're using. And we said the slope of that graph was the spring constant, or the strength of the spring. And so we call that an ideal spring. And so all of these equations assume we're dealing with ideal springs, which means for a spring there's a linear relationship between the force exerted and the amount of stretch of that spring.